Hi, my name is Tom Heffel, and this channel is all about helping students learn chemistry. In this video, we're going to continue our series on LeChatelier's principle, and we're going to be talking about pressure changes. Now, if you want to know about concentration, you got to watch the previous video. If you want to find out about temperature, you got to watch the following video, because this video is going to specifically talk about pressure changes when we have a system that's at equilibrium. And not all pressure changes are going to be the same, okay? We're going to change the pressure two different ways. The first way is through decreasing the volume, and then the second way is by adding an inert gas. So we're going to be talking about both those pressure changes. So what I have over here is I have this equation of N2H2 and making NH3. And I'm going to take the N2H2 and NH3, I'm going to add a certain amount of moles into a 1 liter container. Now, if it's a 1 liter container, then the moles divided by the liters tells you its molarity. And since this is a 1 liter container, basically this number divided by 1 is going to be the same number, but as molarity. So I take those numbers and I plug them into the equilibrium expression that I have right here. The NH3 is 0.00272, the N2 and H2 respectively, okay? And I take them to their appropriate exponent based on the equilibrium expression, and I find out that this system is in equilibrium with a constant that's equal to 0.105. Now, what I'm going to do is I'm going to disturb this system that's in equilibrium by changing the pressure. Now, the way I'm going to change the pressure is by decreasing the volume, okay? Now, when I decrease the volume and I'm cutting it in half, okay, well, then all these moles that I have right here are now going to be in a half liter. So I'm going to take the moles, okay? And remember, to calculate molarity, you got to take the moles and you got to divide it by the volume. So I'm going to take all of these moles and I'm going to divide it by 0.5, okay? And what that ends up doing is it ends up doubling the molarity because these moles are now in half the amount of space, okay? So their molarities doubled, okay? Well, let's see what happens when we double these molarities, okay? I'm going to plug everything into this expression, but I'm going to double all these numbers. So instead of 0.00272, my numerator is now 0.00544, okay? Instead of 0.0402, I'm going to have 0.0804. Instead of 0.1207, I get 0.2414. And when I plug all of this in, I get this answer of 0.0262. And this number is not at equilibrium, okay? So when we decrease the volume, okay, and the molarities get doubled here, okay, no longer is this equal to my number 0.105. So 0.0262, this is no longer at equilibrium, okay? So there's going to be a shift, okay, in this equation. And my job is to decide, is this going to shift to the right or is it going to shift to the left based on these values, okay? Well, if this number is 0.0262 and it needs to go up to 0.105, what that means is that the numerator has to increase or the denominator needs to decrease in order to get 0.0262 to a larger number like 0.105. Well, if I increase the NH3 and I decrease the N2 and the H2, that says that this thing is going to be a shift to the right. We're going to make more NH3, we're going to increase the numerator, and we're going to consume the N2 and H2, okay? Now, how can you do this qualitatively using LeChatelier's principle? I showed you with the numbers of why this thing's going to shift to the right, okay? But how can I explain this just qualitatively using LeChatelier's principle, okay? Well, when we decrease the volume, okay, we're going to end up having an increase in pressure. And according to LeChatelier's principle, we need to counteract that disturbance. And the way we counteract that is by decreasing the pressure. So this is going to be my disturbance, and this is going to be the counteraction of what's going on. Now remember, that counteraction is shifting to the right, okay? So the reason why this shifts to the right is because there are less moles of gas molecules on the right-hand side. And if I go from high moles to low moles, that's going to decrease the overall pressure. And we know that because PV equals nRT, and if I solve for P, nRT is equal to V. So if we are able to decrease the moles, the relationship between pressure and the moles, okay, is a direct relationship. So as the moles decrease, that will decrease the pressure. So all I have to do qualitatively is look at my equation and say, okay, this left side has 4 moles and this right side has 2 moles. If I want to decrease the pressure, I got to decrease the moles. This thing is going to shift to the right in order to decrease the moles, which will decrease the pressure, which is the counteraction to the increase in the pressure due to my disturbance. Okay, so I think that was kind of like a lot to take. Okay, the one reminder that I want to remind you of, it's like the only reason that there was this counteraction, okay, was because the equilibrium constant was off. Okay, so when we doubled all this, we got a number that was not equal to 0.105. Okay, now the second way that we could increase the pressure is just by adding another substance. So if I come in here and I add another substance, let's say I add some argon, let's say I add 2 moles of argon, well, this pressure is going to go up, okay? And some people think, okay, just because I add the argon and the pressure goes up, that this thing is going to continue to shift to the right, but it doesn't, okay? And the reason why it doesn't is that these moles, okay, are, if in this 1 liter container, are still at the equilibrium constant of 0.105. Their molarities did not change because I added argon in here. This argon, it's inert, okay? It's a noble gas. It doesn't react with anything. It didn't react with NH3 or H2 or N2 to change this balance of N2, H2, and NH3, okay? And since it didn't change the balance of the N2, H2, and NH3, their molarities are still the same. It's still 0.105 in this 1 liter container, okay? And this system will have no shift, okay? So not all pressure changes are equal, okay? If you decrease the volume, you change the molarities. And if you change the molarities, you're not at equilibrium, okay? But if you simply add argon in here to change the pressure, okay, the molarities of the nitrogen, hydrogen, and NH3 are not changing. There is still 0.0402 moles of nitrogen per liter in this container. I don't care how much argon you add to it, its molarity is going to stay the same. And if the molarities stay the same, the equilibrium constant is going to stay the same. Okay, it's not going to shift. It's still going to be at 0.105, and there's going to be no shift. Okay, so last time to conclude, okay, not all pressure changes are the same. When you change the volume, you change the molarities, and if you change the molarities, then you have your shift to the right. But simply adding an inert gas does not change the equilibrium mixture, and there will be no shift when you add an inert gas. Okay. If you found this information helpful, please give it a like and subscribe. When you add that comment, it does push the information out to other students that are interested in learning chemistry.